Hi, this is Mark Leach with Simpson Math, and today we're talking about the possible rational root theorem. Before we dive into the possible rational roots, let's talk about some division vocabulary. So, looking at this division, we know that 12 divided by 3 is 4, and I can multiply both sides times 3. The 3's would reduce, and we would be left with this. 12 equals 4 times 3. We can put some vocabulary on this. When we divide, it's the dividend divided by the divisor, and our answer is the quotient. So then again, if I multiply both sides by the divisor, we could say that it's the dividend that equals the quotient times the divisor. In this 12 divided by 3 equals 4, we end up with no remainder, or basically a remainder of 0. And we call 4 and 3 factors of 12. So let's take a look at this example. F of x is x cubed plus 3x squared minus 10x minus 24. Well, we've been talking about in behavior and different things like that, so we should know that we're going to have a y-intercept of 0, negative 24 from our constant. From our leading coefficient, which is a positive 1, we know that we are going to be rising on the right. And then from our odd exponent, we know that it's going to be on the left, it's going to be opposite of what's happening on the right. So we're rising on the right and falling on the left. And because the degree of the polynomial is 3, and we take that degree and subtract it from 1, and we end up with 2 terms. So we expect this cubic to look something like this. We're also expecting 3x intercepts. Now we know that we're not guaranteed 3x intercepts. That's not an absolute fact that that's going to happen, but we're expecting 3x intercepts because the degree of our polynomial is 3. We will have 3 complex roots, which leads to us expecting 3 x-intercepts. Recall that our x-intercepts are when we have real roots, as we saw in our last lecture. So to find the roots of the polynomial, we're going to set f of x to be equal to 0 and solve for x. Whenever we solve our polynomials, we always try to factor if we can. Well, looking at this cubic, we see that we can't factor using the AC method like we would with quadratic or even quadratic-like polynomials. But it is a cubic, so we could try factoring by grouping, but you'll quickly see that that breaks down. If we try to factor out the GCF of the first 2, we'll have x times x plus 3. And then the GCF of the second 2 is a negative 5, which does not leave an x plus 3 on the inside. So factor by grouping does not work. So our current factoring skills don't work. But remember that at the end of the day, factoring is just a fancy way of division. So if I knew one of my factors of this polynomial and I divided out that factor, well then I would end up with 2 factors that would produce my original polynomial. So I have this magic hat. And inside of this magic hat are a bunch of options. And so just suppose that in this magic hat, pop out x plus 4. Now, where did this x plus 4 come from? Well, I'll show you later. So what I'm saying is we're going to take our polynomial, f of x, and we are going to divide it by the binomial x plus 4. Now, again, where does x plus 4 come from? Out of my magic hat, of course. I'll show you that later. Notice x plus 4 is a convenient binomial. What makes it convenient is that it has a leading coefficient of 1. Binomials have a leading coefficient of 1 that we're attempting to do division with. We can do synthetic division with it. So we are going to synthetically divide x plus 4 out of our f of x. So here's a quick synthetic division review. So let's set up our synthetic division. If you think about the division symbol that you used in elementary school, take that, turn that upside down, and we're going to create this like long-looking L thing. Some other professors will put a little backwards L in this corner and draw a horizontal line here. That's another way to do this. You'll see in different textbooks or online resources they'll use it interchangeably. I prefer the way on the left. Even some of my in-laws prefer this way on the right. So you pick. As a reminder, in order to do synthetic division, it has to be a 1x plus or minus some constant. With that, you take the constant, flip the sign, and put that on the outside here. So our divisor is this negative 4, or as a binomial, x plus 4. Then take a look at the coefficients of our dividend. So I have a 1 in front of the x cubed, and this 3, this -10, and this -24. Take those values and just put those across the top here. 1, 3, -10, -24. Once you do that, you've set up your synthetic division. So now we're going to do what Snoop Dogg tells us to do, which is drop it like it's hot, then multiply and add. So take this first one, drop it down, and then just rewrite it. So we're going to have a 1 in that first position. Then we multiply our divisor and this value from the quotient, multiply them together, and we get -4, and put it in the next column. So again, we're going to drop it down, then multiply these together, and get this -4, and then add them up. So when we add them up, 3 minus 4 is this -1. Then we repeat the process. Multiply, and we get 4. Add it up, and we get -6. Then multiply, -4 times -6 is 24. And -24 plus 24 is 0. So, because I picked this out of my magic hat, very suspiciously, we ended up with a remainder of 0. Since we got a remainder of 0, then that means that x plus 4 is a factor of our original polynomial, f of x. But on top of that, our quotient is also a factor of f of x. Now, what is our quotient? Well, there's two ways you can think about this. First up, you can think of this out. We started with a cubic. We divided a linear term out of it. So now we're down to x squared, then a linear, then a constant. So basically reduce all the exponents by 1. So in the far left column, it's now an x squared, then it's a linear term, then it's the constant. The other way to think about it is that in this last section, this is our remainder. So if that's our remainder, then the term next to it is going to be the constant, which has to be x to the 0. Then next to that is the linear. Then next to that is a square, so just go up by 1. So either think reduce all exponents by 1, or understand that we have remainder, and then constant, and then just go up by 1 every time. So just to recap what we did, we took our function f of x, we divided it by x plus 4 evenly, or with a remainder of 0, and got x squared minus x minus 6. Well, if I was to multiply that divisor up, I end up with this f of x is x squared minus x minus 6 times x plus 4. So that means that x squared minus x minus 6 and x plus 4 are factors of this f of x. So that means that we just factored that polynomial. That's awesome. Now, if you look at this, this is a quadratic. So we can pick up where we left off and actually finish factoring this polynomial, because this x squared minus x minus 6, we all should know how to factor. So we can just use the AC method. We see that AC is -6, and our factor pairs are going to be 2 and -3. And since A is 1, then we can just jump directly to our factors of x plus 2 and x minus 3. This x plus 4 sticks around, so when it's fully factored, it's our function f of x is x plus 2 times x minus 3 times x plus 4. We'll set each factor equal to 0 and solve, and we end up that x equals -2, 3, and -4. These are the real roots, or the intercepts, or the x-intercepts. And you can write your x-intercepts as a point. So going from left to right, we have -4, comma 0, -2, comma 0, and 3, comma 0. So recall that we had a y-intercept of 0, -24. We were rising to the right, falling to the left with 2 turns. We were expecting 3 x-intercepts, and we got them. So we can use all this information to easily graph. So if we look at our function here, we have our x-intercept of -4, 0, -2, 0, -3, 0. Our y-intercept of 0, -24. We were rising to the right, falling to the left, and we end up with our 2 turns. Now, don't worry so much about how far down this or how far up these values are going to go. Again, literally, that's calculus, as if we find those points. If you want to plug in a few extra points just to know, you could just plug in a 2 and make an estimate as to where it's going to go, feel free. But other than that, I just care about these x-intercepts, the y-intercepts, and our in behavior and number of turns. Also, I forgot to mention the multiplicity. Since our roots or the factors each show up once, we have a multiplicity of 1. That's how we know that we are passing through each of those. So they're passing through or crossing the x-axis. So now back to the big question. How did I know to synthetically divide by -4 or x plus 4? Well, I used a magic hat, of course. And this is where we get our possible rational root theorem. We're going to make a list of all of our possible rational roots. Let me just break down the words of the theorem first. First, we're creating a list of possible rational roots. So the values that we're about to get in our list, they're the ones that are possible. Okay? So if it's a number that's not on the list, then it's not a possible rational root. And then also because it's possible, there are going to be many numbers on our list that don't end up being roots, but that's okay. Also, we're finding a list of rational roots. So last lecture, we looked at irrational roots, or even in a few cases, some imaginary roots, imaginary or non-real roots. And those irrational or non-real roots are not going to show up on this list. What the possible rational root theorem does for us, or I abbreviate as PRR, is it's going to generate a list of factors that are possible rational roots. So to find these factors, we first develop a list of our factors of our constant, that last term. We also find a list of the factors of our leading coefficients. We mix those together, and then we also recognize that we could have positives or negative roots. So I'm okay with either positive or negative values of these roots. So looking back at our first example, we take this -24 and we take our leading coefficient of 1 and we develop our list this way. So let's first look at the denominator or the factors of the leading coefficient. Well, if you think about the factors of 1, it's just 1. So my denominator, I just have a simple 1. And my numerator, it's the factors of the constant. My factors of the 24 are 1 and 24, then 2 and 12, 3 and 8, and 4 and 6. If writing it out in a horizontal row like this is tricky for you, it's okay for you to think about like when you do the AC method to jot it down in that order: 1 and 24, 2 and 12, 3 and 8, 4 and 6, and you realize 5 and nothing. And so then you know that you have all your factors, and then just write them down in order from least to greatest. So we write down our factors. I'm going to put each value in the numerator over each value in the denominator. And since we just have the one value in the denominator, our list is really just a list of the factors for that constant. So we can have 1, 2, 3, 4, 6, 8, 12, 24, or -1, -2, -3, -4, -6, -8, -12, -24. So notice there are 16 possible rational roots. Instead of me just telling you, poof, x plus 4 or the root -4 was a factor, if we were to use the possible rational root theorem, we would see that inside of our hat, we have 16 numbers. And then you could just randomly pull out one of them and test it. So if I was to pull out this -3 here and test it, I would not have ended up with a remainder of 0. But I could have just as easily pulled out this root of 3 or x minus 3, or this root of -2 or x plus 2, and that would have also worked. And then I would have had a different quadratic to factor, but I would have ended up with the same set of roots. What's amazing here might seem a little silly, but that is we went from me looking at the function f of x and thinking to myself, oh my gosh, there could be an infinite number of possible rational roots, infinite number of values that could be my roots. But through the possible rational root theorem, we narrowed it down from an infinite number of roots down to just 16. Down to something a whole lot more manageable. So let's take a look at g of x and be able to apply the possible rational root theorem this way. So g of x is 2x cubed minus 5x squared minus 6x plus 4. So let's apply the possible rational root theorem to build our list of possible rational roots. So let's take a look at our constant term, which is 4. And the factors of 4 are 1 and 4, and 2 and 2. Thus we don't need to write the 2 twice, so we just have 1, 2, and 4. And then our leading coefficient is this 2. So the factors of 2 are 1 and 2. I need to take our ratios here and turn them into a singular list. I'm using air quote distribution. So not really distribution, but that sort of idea. So first, just pretend that 2 is not there, and I'm only looking at that 1. And if I do that, I see that I have a 1 over 1, I have a 2 over 1, and I have a 4 over 1. And that's where I get my 1, 2, and 4. And then, once I know that I've dealt with that 1 in the denominator, pretend that's not there, and all I have is a 2. So then this way I have a 1 over 2, which is 1/2. And then next I have a 2 over 2, but 2 over 2 is just 1, and I already have that 1. I don't need to write it twice, so 1's already accounted for. And then lastly, I have 4 over 2. 4 over 2 is also just 2, which is on our list, so we don't need to include that in our list anymore. So I have 1, 2, 4, and a half, but also -1, -2, -4, -1/2. So we have 8 numbers to test to see which of, if any, of these 8 are my rational roots. Because this is a cubic, we know that we're going to have 3 complex roots. So all 3 of them could be rational roots. I could end up with maybe only just 1 rational root and 2 irrational roots. For that matter, I could actually end up with 3 irrational roots. I'm not guaranteed that I have any rational roots. So keep that in mind as you're working through this, that this is a list of, again, the possible rational roots. If there is a rational root, it is in this list of 8. So I have 8 numbers to try. I can pick any of them in any order. Doesn't really matter. Often the 1 or the -1 is pretty easy to do mathematically, but they may not be our rational roots. So I'm just going to pick the 1. So picking 1, I can do my synthetic division. So I drop down the 2, and I get a 2 down in my quotient. 1 times 2 is 2. Add them up, you get -3. 1 times -3 is -3. Add them up, you get add -6 and -3 up, and I get -9. 1 times -9 is -9. Add 4 and -9 up, and we get -5. Now, is -5 0? Absolutely not. So this tells me that 1 is not a root. It also tells me that the factor x minus 1 is not a factor of g of x. So I can eliminate 1. It is no longer valid. I pulled it out of my magic hat, but it's not one of my roots. So pick another one. This time I'm going to pick 1/2. So let's see what happens when I try 1/2. So again, we drop down our 2, and I have a 2 in my quotient. 1/2 times 2 is 1. Then add them up. -5 plus 1 is -4. Then multiply. 1/2 times -4 is -2. Now add it up. -6 plus -2 is -8. Now we multiply. 1/2 times -8 is -4. Then add 4 plus -4 is 0. So ta-da, we found that since we got a remainder of 0, that means that 1/2 is a root of this function, and that means that x minus 1 is a factor, as is 2x squared minus 4x minus 8, which is our quotient. Again, we had a cubic. Our degree of our original polynomial was a cubic. So just reduce the exponents by 1. So we have a square, there's our linear term, and then our constant term. Or you could start with our constant term and then work your way up. Now, just this little bit of technical note, there's something called a remainder theorem. Don't stress too much about it. I'm not going to ask any questions about it on our upcoming test over this, but there's this idea about a remainder theorem. So it says that whenever I use synthetic division and I divide these values out, the value that we get as a remainder is actually the y value that I would get if I just plugged in the number. So for example, I divided out this 1 or an x minus 1. When I did, I got a remainder of -5. So that tells me that 1, -5 is a point on my graph. If you're not sure, test it out. Plug in a 1, you'll see that we do end up with -5. That works for any number in our original function. All right, so after our division, we're going to simplify and restate what g of x is. So since we're finding the roots, let's replace g of x with 0. And then I can rewrite g of x as my factors. So my quotient, 2x squared minus 4x minus 6, times my divisor of x minus a half. And that's what we have here. Then as we solve, we can factor out that 2, because I noticed that this trinomial has a GCF of 2. So factor it out. And actually, let's just go ahead and get rid of it by dividing both sides by that 2. So now it's just 0 equals these two factors. If you take a look at the factor, x squared minus 2x minus 4, that's not factorable, or it's not nicely factorable. If we tried to factor it, AC is -4, and my factor pair is 1 and 4, 2 and 2. And no matter how you apply the negatives, you're not going to get a sum of -2. So it's not factorable, but it is a quadratic, so we can solve it using the quadratic formula. So let's do just that. I can use the zero product property to separate my two factors. So I can go ahead and say that x equals 1/2. I like to put a little oval or circle around it to saying, hey, that path has stopped. I found a value of x, but I don't want to forget it. I'll come back to it. So we know that one of our factors is x equals 1/2, as we knew after we did our synthetic division. So for our quadratic formula, a is 1, b is -2, and c is -4. I plug in my values into the quadratic formula. I like to do my discriminant on the side. It just makes my life easier. So if I square -2, I get 4. -4 times 1 times -4 is a positive 16. That adds to be 20. And I can simplify that 20 to be 4 times 5, which is 2 square root of 5. So I'm going to replace that square root with 2 square root of 5. And then I will unadd these fractions. So as an in-between step here, this would be 2 over 2 plus or minus 2 square root of 5 over 2. So that way these 2's reduce to 1. These 2's also reduce to 1, leaving 1 plus or minus square root of 5. So I have 3 roots. I have my positive 1/2. I have x plus square root of 5, and then x minus square root of 5. So my x-intercepts are just that, but comma 0. So 1/2 comma 0, 1 plus square root of 5 comma 0, and 1 minus square root of 5 comma 0. I'll skip this note for just a second. Let's go ahead and graph. Earlier I skipped over it, but you should pretty quickly be able to determine that our y-intercept is 0, 4. We are rising to the right because the leading coefficient is positive. Our exponent is odd, so it's going to go in the other direction. And we were expecting 3 x-intercepts, and we got them. All right, looking at graphing this, I'm not going to make a too big deal about this because we've been doing it over the past few lectures, but we see that it's rising to the right, falling to the left. We have our y-intercept, and we graph our 3 x values. I've even included the 1 comma -5 that we got from the remainder theorem. So that's how we graph that function g of x. Let's do another one. Let's graph h of x is x to the 4th minus 3x cubed minus 20x squared minus 24x minus 8. Let's quickly grab our graphical information. We understand that the y-intercept is 0, -8 from our constant. Because it is a positive leading coefficient, we are rising to the right. And because the degree of our polynomial is 4, we're going to be rising to the left. And then because it's a 4th degree polynomial, we expect 3 terms. We might not get them, but we expect those 3 terms. And we're, again, 4th degree polynomial expecting 4 x-intercepts. So when we are trying to find our x-intercepts, we're going to set the function equal to 0 to find our x-intercepts or our roots. Now let's do the possible rational roots. So take a look at the constant term, and let's write our factors. Well, the factors of 8 are 1 and 8, and 2 and 4, and we write them in order 1, 2, 3, 4. And our leading coefficient is a positive 1. So if I pair up the every numerator with every denominator, I just get 1, 2, 3, 4, but both positive and negative versions of that. So we end up with 8 numbers to choose from. Pick one of them. As you see here, I have I tried 1 just to show you what 1 would look like. It does not work. But this does tell me that 1 comma negative 54 is a value on the graph. So now I'm going to test -1, and it does work. So x plus 1 is a factor. And then when I convert our quotient numbers into the actual polynomial, it's going to be x cubed this time, the minus 4x squared minus 16x minus 8. Recall if for some reason that, let's say that there was no cubic term in the original polynomial, if this was not there at all, there was just a 0 coefficient, then I would have a 0 in its place. So to make sure you still have a value in every placeholder. So this tells me that x plus 1 and x cubed minus 4x squared minus 16x minus 8 is a factor. So we can express it this way. So if I can factor it out here, I can use the zero product property to separate these out. So this tells me that one of our roots is x equals -1, which we knew from our synthetic division. But now if you look at this big polynomial, that's not a quadratic. If it was a quadratic, we could factor it, we could quadratic formula, but we don't have the means of solving this. We could try factor by grouping, but it's not going to work out. So we're going to have to continue this process again. Just repeat it. So since it's not factorable, we're going to need to return to our magic hat to find another possible rational root. When forming your list, there's just a few notes. One, you could create a new list of possible rational roots. But when I did it this time, it doesn't make a difference because our constant term and our leading coefficient didn't change. But often if the constant or leading coefficient changes, then your possible rational roots list got smaller, and that's just going to make your job a little bit easier. On top of that, I can eliminate +1. If +1 was not a root of the big polynomial, it's not going to be a root of the smaller polynomial. But remember though, -1 could be another factor because there could be a double root at -1, so that's not off the table. So really at this point, we have 7 numbers to pick from, not +1, but -1, then plus or minus 2, 4, and 8. So I tested -1 to see if there was a double root. We did not get a 0, so that is not a double root. At this point, the remainders of these values are not values on the function. If I was to just graph this cubic, then yes, -1, 3 would be a value on that graph. But I'm trying to graph h of x, not this factor. So let's say I test 2. Again, I don't get a remainder of 0, so 2 is not a root, or x minus 2 is not a factor. And again, in this case, 2, -48 is not on the graph. I would have to have tested 2 on my original function. Now let's test -2, and I do end up with a remainder of 0 when I work through my synthetic division. So it tells me that x plus 2 is a factor, along with the quotient, x squared minus 6x minus 4. Notice I went from a cubic down to a quadratic. So I can take my cubic and break it apart into its 2 parts. And I see that we have x plus 2. So one of my roots is going to be x equals -2. And since x squared minus 6x minus 4 does not factor, I'll need to apply the quadratic formula. So I work through the quadratic formula, and I get 3 plus or minus square root of 13. So if I was to so don't forget, okay. So putting this all together, our x-intercepts are -1, 0 from our first division, then -2, 0, then 3 plus square root of 13, and 3 minus square root of 13. We have our x-intercept of -2, 0, -1, 0, and for the 3 plus or minus square root of 13, we go 3, and then plus just over 3.5, and then minus just over 3.5. We also have an x-intercept of -8. But I included the second one for you to see how far down this goes. Polynomials can get quite tall. And in fact, also we have that 0.1, -54 is on the graph. All right, guys, I just want to reinforce what we're doing. So we're taking the polynomials and factoring them. That's it. We're basically this is a different way of factoring. Yes, it feels a good bit longer, but these are more complicated polynomials than you're used to. It's not just the quadratic, not just factor by grouping. Even though, yes, I know it takes a moment, through the possible rational root theorem, we're able to factor these. So look at this g of x function. Ultimately, we could factor it. I could express it as a product of linear factors to be 2 times x minus a half times x minus 1 minus square root of 5 times x minus 1 plus square root of 5. Now, how do I get that? We'll take a look at this x-intercept 1/2 comma 0. So my x value 1/2, if I was to say x equals 1/2, I could subtract that 1/2 to the other side. X minus a half is 0, and you should be able to see that that is one of our factors. I do that to each of those. So it's x minus 1 plus square root of 5. Distribute that negative, so it's x minus 1 minus square root of 5. Do the same thing to 1 minus square root of 5, and that's how I get x minus 1 plus square root of 5. If I was to FOIL these two binomials together, I would end up with x squared minus 2x minus 4. And then if I was to multiply all of these together, I would end up with the original g of x function. So we are literally just factoring. Looking at the h function, the same thing happens. We're basically factoring h of x into these 4 linear factors. So my -1 and my -2 lead to the factors x plus 1, x plus 2. 3 plus square root of 13 is a factor x minus 3 minus square root of 13. And 3 minus square root of 13 is x minus 3 plus square root of 13. Again, if you were to FOIL these two together, you would end up with our x squared minus 6x minus 4. And if you were to FOIL all of them together, you would end up back with your original h of x function. So there you have it, the possible rational root theorem. We use the possible rational root theorem to magically create a list of our possible rational roots. We test them one by one until we find ones that work, and those are our factors. I hope this helps you be able to do your homework and to ultimately be successful in college algebra. Until next time, I'm Mr. Leach with Simpson Math. Have a good day.